So here is that formal analogy. So it was asked in this paper, maybe you could somehow formally think about the area of the horizon of a black hole as somehow an entropy, but surely this is not possible, because if they were, it would radiate, and that can't be true, because all things fall into black holes and nothing ever escapes. I said that twice, because you would certainly think this is true, and this is where a series of paradoxes are going to arise. So enter quantum mechanics. So far, I've talked about, space-time and the structure of space-time, the physics of the first half of the century, of the previous century. At the same time that general relativity was being discovered and developed, at the same first half of the last century, quantum mechanics was being developed and discovered. Now, what does quantum mechanics say? So quantum mechanics, which a priori seems to have nothing to do with general relativity and gravity, says the following things. That first of all, the first statement is that microscopically, the world isn't classical, it's governed by quantum mechanics. So what does that mean? So look, so in classical physics, if, there's me and I'm going to throw a ball to Matt over there, I throw the ball and it follows a trajectory, and there's Newton's laws that tell me what the trajectory is, and it lands in Matt's hands. There is a given trajectory it follows. But in quantum mechanics, the rule apparently microscopically says that if I tell you that a ball went from A to B, then it has some probability, technically something called an amplitude, but anyway, a probability of taking any conceivable path from A to B. It could go to the moon and then go back down to Matt's hands, or it could go straight, it could do whatever it wanted. It's just that each of these things has a certain probability or amplitude, and they can interfere and cancel, and all kinds of things can happen. And the classical trajectory that we usually see is just the one that's most likely. Now, that is also a very strange concept. No stranger or no less strange than the warping of time by matter, according to general relativity. And if you want to have some sort of qualitative feeling for what this means, I would advise reading a story called The Garden of Forking Paths by Jorge Luis Borges. So this is a very beautiful story. And the final page of the story was the epigram to the PhD thesis of Hugh Everett, who invented the many worlds formulation of quantum mechanics that described this. So I would read that story. It will give you a very vivid sensation of what this idea is about. So amongst the other things that you learn from quantum mechanics is that energy can kind of change quantumly into other forms. Just like a thing can go from one place to another place through many different paths or different amplitudes. If I told you in my hand I have a joule of energy, the joule of energy can spontaneously fluctuate into anything else that has a joule of energy. It just has some chance of doing so. So for example, if you have energy in a gravitational field, it can spontaneously become a pair of an electron and a positron and then turn back into gravitational energy. That's an allowed process in quantum mechanics. And there are so many, there's 100 years of experiments verifying in ample detail that this is all true. Right? It's just absolutely true. So this is all true. So in 1975, Hawking said, well, look, we have quantum mechanics and we've got classical gravity. Surely we should do both together because the universe has classical gravity and it has quantum mechanics. So he considered the following situation. So this is a picture of a black hole, artistically drawn horizon, these little dashes here. And you imagine that just outside the horizon, the energy in the gravitational field spontaneously fluctuates into a particle and an antiparticle. One of them falls in behind the horizon, and poor thing can't escape anymore. So you're left with a particle left alone now, and what can it do? It escapes off to infinity. So all of a sudden, because of quantum mechanics, because the microscopic nature of the universe is quantum, a black hole, which you would think classically can only grab stuff, cannot radiate stuff, instead radiates a particle. Even more amazingly, Hawking showed that at the level that you could do the calculation, at least at the time, this radiation looked precisely thermal with the temperature required to make this analogy between black holes and thermodynamics exact. That's an amazing thing. Amongst other things, it's amazing because it means that quantum black holes evaporate away if you don't keep feeding them. It's not true that they trap stuff forever, but there's a catch. The radiation, as I said, looks thermal. Thermal radiation is random radiation. Thermal radiation is as random as possible consistent with the conservation of energy. There's no structure in it at all. So that's the kind of radiation that seems to come out of black holes. So that lands us on a paradox. Here's the paradox. I'm going to give you 3 versions of the paradox. Version 1 of the paradox is like this. You make a black hole from elephants or from dictionaries, and you put them into the, and there you go. The black hole is sitting there, it's in a box. There's no way to tell from outside what the black hole is made of, so you might say that the information is erased. Yes, so you might object, as this gentleman here said, saying, well, it's just hidden. It isn't erased. So then you go to version 2. You make 2 black holes of equal weight, one from collapsing elephants, the other from dictionaries, and you let them both evaporate. The radiation is thermal, and the temperature only depends on the mass and not on what the black hole was originally made of, whether it's elephants or dictionaries. So in the end, when the black hole's gone and evaporated, the information is erased. That's a better version, yes? So here's version 3. Let's make this even more stringent. I'm going to start the universe in a state of 0 entropy, no entropy at all. So that's called a pure quantum state. You're going to let the matter in this pure quantum state collapse to make a black hole, and then you collect the radiation in the box as it radiates, as it comes out. The entropy of the radiation, the disorder in the radiation, keeps increasing with time because, as I told you, the radiation is thermal. And if it's thermal, it means it looks random. And so you're collecting this random radiation. It's as disordered as possible. And so eventually the black hole is gone, and the entropy went from 0 to some very large amount. And so because you've increased the disorder, the information in the system was erased. So these are 3 versions of the statement that black holes, that putting quantum mechanics and black holes together causes you to have a paradox in this sense of losing information. So you might say, is that really a paradox? And it is. The reason it's a paradox is, well, the pillars of 20th century physics are general relativity and quantum mechanics. Here are some basic principles required for the self-consistency of quantum physics. First, quantum systems are described by the probability, more technically the amplitude, that they are in any given configuration. That's what I was describing earlier. Second, quantum systems can be uniquely evolved forward or backward in time to derive the probability of any configuration at any time. So if I tell you what is the state of a quantum system now, there is a deterministic rule that tells me the state for all future times and for all previous times. That has a consequence. The consequence is that in a precise sense, quantum systems do not erase information. It's not possible. It's a theorem. So now, we just argued that if you put general relativity and quantum mechanics together, you have information erasure. Something's just wrong. You can kick out quantum mechanics, you can kick out general relativity, you can kick out both, you modify both, something has to give. Because otherwise, you have a problem with the edifice of physics. Okay. So, well, so I'm a string theorist. And indeed, I started going into the field of string theory because of this paradox, because this seems so strange. And it's good to have paradoxes, because they give you pointed questions that you can try to answer. So the job of theorists is to imagine ways out of these problems. And a conservative answer to this problem is don't throw out quantum mechanics, don't throw out general relativity. Actually, there's some kind of secret argument for information recovery, and there's a reason why we couldn't see it before. So let's investigate that. So here's an argument for information recovery. So let's suppose that I have a black hole that is in some particular microstate, some microscopic configuration, that is determined by whatever originally made it. Right? That could be black holes, that could be elephants, that could be dictionaries, whatever it is that we used to make the black hole in the first place. Now here are some 2 further theorems from general relativity and quantum mechanics. In quantum mechanics, every state, it's a theorem, that every possible state that you have, every unique state, has a unique energy or mass up to the symmetries in the problem. We're going to ignore the symmetries for now. Okay? So that means every state in the system has a unique mass. Now here's a theorem from general relativity. The energy or mass of a system can always be measured from far away by testing how much space warps as you approach the system. In fact, that's the qualified general relativist measures mass in this way. You have a thing over there, you walk towards it, and you ask how much the warping of space changes, and that tells you how much mass is there. So that's what you're supposed to do. So now I'm going to say, put these two statements together and come to the following conclusion. Suppose you have quantum mechanics and general relativity. Every state of the system, including the black hole, has some unique mass up to symmetries. And then you measure the mass very carefully from outside the black hole, and you uniquely determine its state. So what's with the information loss? The information is never erased. How can it possibly go away? That seems like a very good argument, but it seems too easy. Why was there such a head-scratching paradox? Here's why. So let's ask ourselves, well, that's very nice. So you can measure the mass to measure the very carefully, and you would know the state of the black hole. You could avoid these paradoxes. But precisely how well do you have to measure the mass in order to be able to get around the supposed paradox? So we already said that Hawking, Bekenstein, and company argued that the entropy of a black hole is proportional to the area of the black hole. There's actually also constants, Newton's constant and Planck's constant and other things. So what that means is that there's a very large entropy. Okay? So according to the standard rules of physics, if you have so much entropy, it means that the number of states that you're talking about is exponential in the entropy. That's what it means to have an entropy. There's lots and lots of different microscopic configurations that look similar. That's what it means to have an entropy. So now let's suppose that you are capable of making a measurement of the mass of the system with a precision delta m, some tiny precision. Then the statement that the black hole has this entropy means that between the mass m and the slightly different mass delta m, that's the resolution of the measuring device, you need to have exponentially many states of the system. But that means to space out so many states, their spacing, their separation energy must be tiny. I'm packing so many different states within such a small range, they must have a very tiny spacing. Now we can put in another theorem from quantum mechanics. It's called the time energy uncertainty principle. Remember, you will have all heard that in quantum mechanics there are these uncertainty principles between, there's been energy and time, momentum and space and things like this. And the time energy uncertainty principle says that if you wish to measure energy with the precision delta E, then the amount of time it takes, delta T, that's the amount of time to make this measurement, is related inversely to the energy precision. So what that means here is the amount of time you need goes exponentially in the area of the black hole divided by constants like Planck's constant. So that was a somewhat technical argument, but the reason I gave it is, this is just a little bit of algebra. But what it immediately tells you is that in order to make a measurement of the mass of a black hole with the precision required to tell precisely what its microstate is, you would need longer than the age of the universe. So that's why this is hard. If we did any kind of approximation, so I have a real device, I'm going to sit there for 3 years and make a measurement, it's just not going to work. It's going to be hopelessly inadequate. So it would appear that what's really going on here is that the information is there about the black hole, but it's very difficult to decode. In this language, it takes a long time to decode. There's something about it that's very complicated, very complex, and hard to decode because of that. So let's think about that. So to do that, to think about that in a concrete way, you need some way of thinking about what are the actual physical states of the system. How do you construct the microstates of a black hole? So I'm actually going to give you the sort of two-slide introduction to decades of string theory here. Okay, so we want to construct now the quantum states of a black hole. And I'm actually going to do this. This is only for the technical my brethren in the field, so they don't complain to me afterwards. We're going to do this actually, strictly speaking, in a universe with a negative vacuum energy as opposed to positive vacuum energy as it is in our world. That's a technical simplification that helps my colleagues. I'm saying this so that Matt here doesn't complain to me afterwards. But you don't need to know that. Anyway.